In our last class, we introduced the concept of moments. So we had said that we know that forces are vectors, and vectors mean that they have magnitude and direction. However, sometimes in the study of statics, we need to look beyond just magnitude and direction of a force. We also need to consider the location of that force. We mentioned that the reason we need to consider that location is because depending on where a force acts on, it's going to result in a tendency for rotation. In other words, if my force acts on an object, and this is just a review of last class, then that force is going to result in a tendency of rotation around a point of interest. We mentioned that if that force was at a distance, which I'm just going to call d, for distance, from my point of interest, then the moment could be calculated by taking the product of the force and the distance. Now, we mentioned a couple of things that we wanted to be aware of before we went knee deep into this subject. First off, the distance is actually the distance that is perpendicular to the line of action of a force. And when I say line of action of a force, I mean that line, that infinitely long line through which my force vector acts on. So here's where I think we're going to have most of our problems with moments. I think it's going to be in determining that distance from the line of action of a force. And in order to look at that, we saw this example with this L-shaped wooden bar that had a force acting at one end of this object. And we mentioned in class that the line of action of that force would be an infinite line that passes through the vector. And we said that if we wanted to find the moment about a point at the wall, in other words, at the other end of our object, then that distance d would be the distance that's perpendicular to the line of action. Now, sometimes that distance and the force intersect. Sometimes the distance will touch the line of action, not necessarily the force vector. But remember, these force vectors, these are not real lengths. These are just representations of the magnitude of the force. So you shouldn't think of these force vectors in terms of them being this long or short. Instead, you look at these lengths of those vectors as the magnitudes of those vectors. We mentioned that if we did not want to, or if we didn't have the tools necessary to calculate that distance d, then we could, instead of trying to find the distance d, we could split the force up. So I'm going to draw my force vector again, but we could split this force vector into its x and y components. Now, from our initial courses on vectors, we've already learned how to find these x and y components, and we can find them using some geometry, right? For the most part, we're going to use trigonometry to find these components. But in general, we will be able to find it using things like similar triangles, trig identities, the unitary circle, and so on and so forth. But what was the point, right? The point of finding these x and y components is that now I can find my moment about my point O by looking at the moments or the individual moments that each of these components causes about this point. In other words, my line of action for my y force is this vertical line. And therefore, the distance between this point and my line of action is simply this horizontal distance, which I'm just going to call A. And A is a distance. Likewise, my line of action for my x force, x component of the force, is this horizontal line. And the distance between my point of interest and this horizontal force is this one, which I will call B. Now, following this formulation, my moment then becomes my x component of the force multiplied by the distance between my point of interest and the line of action, that is B. and my y component of the force multiplied by the distance to this line of action, which we call A. Now, of course, here's where things start to get a little bit tricky. We need to come up with some sort of sign convention so that we can add and subtract moments properly. And we mentioned that for this class, we're going to take our positive as counterclockwise, our negative as clockwise. If you forget about these, don't worry. As long as you keep a consistent sign convention, your answer should be okay, but you will need to specify which way your moment is actually causing the rotation about. In this case, my x component of the force causes a clockwise rotation, so I'm going to give it a negative value. My y component of the force causes a clockwise rotation, so I'm going to give it a negative value. Now, of course, I mentioned I don't want you to memorize this equation because this equation will vary, right? That whether it's positive or negative, whether it's A or B, it will really depend on how your system is formulated. So my intention for you is not to give you a set of equations to memorize. It is instead to give you the tools you need to find these equations, because each different system will have a different set of equations. So that was a bit of a review of what we covered in class. We did a little bit of work on moments in 3 dimensions. Where we mentioned that in 3 dimensions, where we're looking at a 3-dimensional space measured in Cartesian coordinates, so x, y, z, moment would be a function of the force vector as well as a position vector. A position vector that tells you the distance between the force and your point of interest. So again, in the case of 3-dimensional moments, we need to think of the following. My forces are vectors, and because they are vectors, they will have 3 components in the x, y, and z directions. And likewise, my position vector is, well, a vector, just like the word says, and we'll have 3 components as well. Now, I mentioned that moment, which is also a vector, can be calculated by taking the cross product of your position and your force vector. Now, this cross product is a vector operation. And this vector operation is going to tell us the potential for rotation between 2 vectors. In other words, this vector operation that we call the cross product quantifies, right? Quantifies the difference in direction between those 2 vectors. And we said that this cross product can be solved by taking the determinant of the 2 vectors. And if you didn't remember the determinant, it's okay. We did a bit of a review on it. The determinant was found by looking at your positional unit vectors, the components of your first vector, in this case r, the components of your second vector, in this case f. So to find the determinant, we're simply solving a 3x3 matrix formed by the unit directional vectors and then the components of the 2 vectors. Now, we did some work here, and if you need a review, you can always look at the video from Monday's class. But I'm just going to skip all the way to the end. We mentioned that to solve these position vectors, this would result in Ry Fz minus Rz Fy in the I direction minus Rx Fz minus Rz Fx in the J direction plus Rx Fy minus Ry Fx in the Z direction. And this, we mentioned, was the expression for the vector form of a moment. Now, as long as you know how to solve cross products, you should be able to come out to this equation. If you need more practice, I would recommend that you just do as many homework problems and textbook problems as you can, so that you can get used to this formulation. So that's a bit about what we covered. We did an example from the book and all that stuff. But today, I'd like to look at some applications of this form of the moment vector. So today, I'd like to focus on finding moments about a specified axis. And what do I mean when I say that? So for that, let's review first at a bit of our force theory. So from chapter 2, remember that forces are vectors that have an x component, a y component, and a z component. And we also remember that we could actually find components of forces not just along my x, y, and z axes, but I could also potentially find, oops, my lighting is not very good here. Let's see. Nope, there we go. But I could also potentially find components of forces about any axis. So I'm not gonna make you go back to your notes. However, I think it'd be good to review this a little bit. You remember, we said a couple of things. We said that one, any force vector can be looked at as a product of the magnitude of the force times a unit vector along the direction of the force, right? That was one of the ways we looked at forces. But then we also said that we could use properties like the dot product, right, to find forces directed along an axis. In other words, force components along an axis. In other words, if I have a force, this is simply my force X, or sorry, my force F. And I would like to find the component of force F along an unnamed axis. Can anybody give me a letter? I just want something to identify this axis. Any ideas?
You could use V.
V? Okay. So if I want to call this axis V, if I want the component of this force along my V axis, that essentially means that I'm looking for the projection of the force. And so if I'm looking at this vector from above, then the projection of this force along this V axis is simply my force component. Now we can call it F sub V, or as we did in class, we could also call it F parallel, because it was the force component that was parallel to your axis of interest. Now, why am I bringing this up? Because now we know that we can find such a component two different ways, right? We could first figure out the angle and then use some trig identities to find that force. Or another way we could find that component was by figuring out first what the magnitude of this component was. Now, if we don't remember how this works very well, I think it would be very good to go back and review a little bit of our forces. But one thing that we managed to agree on was that we could find the magnitude of this parallel vector by using the dot product. And the way we used the dot product was by finding, right, the dot product between this force vector and a unit vector along your axis. So in this case, my axis is V. And if I could define a unit vector, I'm just going to draw it in blue, a small vector with a magnitude of 1 that acts along that axis V, then the dot product of F and UV is simply the magnitude of my force component. But this is only a magnitude. How can we turn this magnitude into a vector? Well, we go back to our definition of a vector. Remember that I always want you to look at vectors as products of magnitudes times a unit vector in their direction. Therefore, the vector form of this component will be equal to its magnitude times a unit vector in the direction that I want. In this case, it's my direction V. And if you look at this, essentially what this tells me is that the force component vector is equal to my magnitude. And you see that the magnitude is simply the dot product multiplied by my unit vector. And this was how we found components of forces along any specified axis. So as long as we know the axis and we can find a unit vector along the direction of the axis, we can find a force component vector. Now, why am I reviewing this? I'm not really going back to this because I want to go back to vectors. However, we will find that knowing this is going to be actually useful for us when it comes to moments. Because just as force vectors can have components along any direction, so can moments. Moments, as you see, are vectors, and vectors can be formed by combining components. So I can find the moment, that is the rotation that a force causes about any specified axis, the same way that I would find my force components. Now, whenever we're dealing with moments and whenever we're treating them as vectors, I know things can get a little bit confusing and a little bit hard to grasp conceptually. So I would like for you to remember, just as we view a force as simply vector sums of different components. So for example, we can view this force as a vector sum of an x component and a y component. So too can we view moments as sums of these components. However, when we're talking about forces, these magnitudes, these lengths of lines, essentially represent how strong you are applying your force. But when we're talking about moments, these magnitudes, these lengths of these vectors represent how much potential for rotation you have. And it may seem confusing, but remember, even for forces, these vectors don't represent lengths. They represent a measure of strength, right? So for moments, these vectors don't represent length. They represent a measure of rotation. So it may be a little bit hard to grasp mathematically or conceptually. I agree. And this is one of these cases where we're going to have to look at various applications in order to fully grasp it. And in my opinion, the best way to grasp this, if you can't get it at the beginning, the best way to grasp this is to look at different types of problems. Now, the good thing is that your book has a lot of problems, and those problems look at different applications. They are told from different perspectives, and hopefully this will help you grasp it. But if you cannot, we'll find a different way of figuring out how to grasp this conception. But for now, what I would like for all of us to agree is that moment vectors can be seen as sums of their components. Now, that being said, we can find the moment about a specified axis just like we would find a force about a specified axis. So let's think of it this way. If we have a moment vector, and remember that this magnitude simply represents a tendency for rotation. And I wanted to find the component of this moment along my unknown axis. I'm just going to call it V again. If I wanted to find the component of my moment along my V axis, I would essentially have to go back to our force formulation. So just to do a quick review, we can find this component by first finding the magnitude of the component, which is the dot product of your force vector and a unit vector along that direction. So let's do that. We can find the magnitude of this component, which I'm going to call M sub V, as the dot product of your moment and a unit vector along the direction of your axis. Now, what is that unit vector? Remember, a unit vector is a vector. I'm just going to draw it here on the side, a vector with a magnitude of 1 in the direction of the axis that you would like to study. Now, we mentioned, once again, that in order to find the vector form, the Cartesian notation of my force, I have to take this magnitude, this f dot uv, and multiply by the unit vector, that is uv. So I have to do the same here. If I want to find my moment, I have to take this magnitude m sub v and multiply by my unit vector u sub v, which is the same as saying the dot product of m uv multiplied by my unit vector uv. So I hope we realize, right, that we are essentially following the same procedure that we would have found for a force. Now, we could solve this by first finding the moment and then applying these terms. So let me look at a quick example, and this will be perhaps let's do an example similar to one from your book.
Professor, just to clarify really quick,
Yeah,
so shouldn't the magnitude of v times the unit vector v be vector mv instead of just the vector m?
Sorry, shouldn't the magnitude of which one?
So the magnitude of mv times the unit vector of mv, or v, that should equal the vector of mv, not the vector of m, right?
Oh, you are absolutely right. Here we go.
Okay, I just wanted to be sure.
No, I forgot to write that subscript there. Yeah, so this is simply the vector form of this component, okay? So let me go ahead and grab my book. And in Monday and Tuesday's class, we looked at a fundamental problem where we had to find a component along the x-axis. And we did using just finding the moment. However, now I would like to look at the next problem. Okay, so we're going to look at problem F4-14.